Thank you very much, Kali, and thank you for giving me this opportunity to speak about our recent works. And as you might already guess from the title, what we focused on in our experiment in Florence recently is the study of the superflow of ultracold atomic superfluids in a ring geometry. And in particular, today I would like to speak about two different experiments on the realization and the study of the stability of persistent currents in this kind of system, and on the study of Kelvin-Helmholtz instability still in ring geometries. So let me start from the very basics. Okay, I'm sorry. So as we all know, superfluids are very different from classical fluids, for especially what concern rotation. So a superfluid, a medium that it's invested has an irrotational displays an irrotational flow under rotation. And this mathematically means simply that the rotor of the velocity of the superfluid has to be 0, simply because the velocity of the superfluid is proportional to the gradient of the phase. But this is not just a mathematical constraint on the motion on the superfluid, because it really changes dramatically what happens when we put a superfluid under rotation with respect to a classical fluid. That here I sketch with this simple cartoon. So as we know, when we put under rotation a classical fluid, because of the friction, the classical fluid changes its shape and starts to rotate, let's say smoothly enough. On the other hand, when we set a superfluid into rotation, this kind of medium develops quantized vortices. And the reason why the superfluid under rotation admits the presence of quantized vortices is given by the fact that the circulation in superfluid has to be quantized. So the circulation is defined simply as the integral of the velocity over a closed loop, and to have a single valued wave function of the superfluid, and so well defined over all the medium, and in particular on the path that we are exploring, the circulation has to be quantized on a multiple of 2 pi. So I will say it a bit better. So given the expression of the velocity, which is proportional to the gradient of the phase, the circulation has to be proportional to the difference of phase on the 2 edges of one point that we take over this integral. And so for the wave function to be single valued, the difference of phase has to be a multiple of 2 pi. And so the circulation itself has to be quantized. In particular, this W, which counts the number of the winding of the phase around the loop that we have considered, is called the winding number. And the quantization of the circulation in a superfluid may give rise to the fact that the excitation that a superfluid under rotation can display are topological excitation, in the sense that they can survive only in a multiply connected geometry. So what I mean by a multiple connected geometry means that, the density of the superfluid has to have a 0. And if we put a superfluid under rotation, let's say an homogeneous superfluid under rotation, then this topological excitation appears in the form of quantized vortices, where the multiply connected geometry is created by the appearance of a vortex that has a 0 in the density in correspondence of the vortex core. Or on the other hand, we can have excitation at a non-zero circulation in a multiply connected geometry as a ring. So if we impose the multiply connected geometry externally, for example, via the trapping, then we can have topological excitation in terms of currents in this geometry. So here I would like just to show how this kind of excitation look like in the different superfluids that we can have. So for example, for what concern the quantized vortices, they have been, as we all know, observed experimentally, both in neutral superfluids as for superfluid helium and atomic condensate, and in charged superfluid as superconductors when they are exposed to a magnetic field. And in all these cases, they appears as holes in the density of the superfluid that here we can clearly see in these images. And on the other hand, for what concerns the currents, so in this case, we are dealing with a ring geometry as the one that is shown in here, and then that we can trigger in many different ways. And here I give a summary of what are the experimental procedure that we can have in the for atomic condensate, so for neutral and atomic and ultracold atomic condensate. So as I already told you, what we are interested in is exactly the persistent currents, and those kind of excitation despite vortices, quantized vortices, they appears as, let's say, the same excitation in both neutral and charged superfluids. The persistent current has a slight difference. So for example, so what I mean, to be more precise, is that if we consider a superconductor pierced by an external magnetic field, then in this system, the persistent currents represent the new ground state of the system. On the other hand, when we excite some persistent current, some current, let's say, in atomic ring condensate, these are only metastable states on the energy landscape of this system. And here we can understand the nature of the persistent current with this sketch of the washboard potential, where the energy of the system is plotted as a function of the total angular momentum in the system. So in this case, you can see that there exist many metastable state at finite winding, but these are not the system ground state, because anyway the overall ground state of the system is the one with zero current. So in neutral superfluids, we expect the persistent current not to be absolutely stable, but to show a metastable character. And this has already been observed, for example, in Bose-Einstein condensate with atomic condensate, as you can see here in this experiment in 2012, where a persistent current of winding number 3 was excited, and then you can see that just waiting in time and monitoring the presence of the current in the system, there you can see that there are some jumps that represents the decay of the persistent current, and that show clearly the metastable character of these currents. So what I would like to discuss about today is the study of the stability of these currents in atomic condensate, and in particular on the system that we have in Florence, which is atomic condensate of fermions. So in particular, I would like to present you two different conditions that we have explored recently. So the first one is a study of the stability of persistent current and the excitation of the persistent current in two slightly different geometries. So in a single and simple ring, on the one hand, a clean ring, so the stability of persistent current just in a simple ring, and on the other hand, when we have introduced a local imperfection on the ring to induce the supercurrent to decay. And the second work that I would like to present to you today represents a study of the stability of counterflowing current. So in this experiment, we have created a double ring geometry as the one that is depicted in here, and we have injected a persistent current of opposite winding in the two superfluid ring, and then we have studied the dynamic of the system when we remove the barrier that divides the two superfluid, and the counterflowing currents undergo to the Kelvin-Helmholtz instability that we have measured in our lab. So before going into the details of the experiment, I would like to spend a few words on our experimental setup. So as I told you, in Florence, we work with fermionic atoms, and in particular, we work with lithium-6, which is the isotope, the fermionic isotope of lithium. So we use standard laser cooling and evaporative cooling technique to realize an ultracold sample of roughly 10 to the 5 atoms. And here you can see a picture of our cloud at the very beginning. So let's say at the end of the evaporation, before the further manipulation that I will tell you in one slide. So at the very low temperature that we have, so we work at very low temperature and at high magnetic field, and we populate the two lowest hyperfine states of lithium that we call spin. And at the low temperature that we work in, all the interaction between these two spin states can be parameterized by only one parameter, which is the scattering length. And the very interesting feature of lithium-6 is that we can tune the scattering length by acting on an external magnetic field via a Feshbach resonance. So as you can see in this plot, we can tune the scattering length to be either small or large and either positive or negative, such that we can tune the interaction to be either weak or strong and either attractive or repulsive. And this, the possibility to tune the scattering length allow us to realize and explore the so-called BEC-BCS crossover of interaction strength. And here I show you what is the phase diagram of the BEC-BCS crossover. So we work with these two different spin state of lithium-6 and at very low temperature. And what happened at the very low temperature that we have is that the two spin atoms, these two different spin can form a couple, and the couple that they form depends on the interaction that they feel. And in particular, when the interaction are weak and repulsive, we have tightly bound molecules of lithium atoms, and so we can then undergo to Bose-Einstein condensation, and so we can produce a Bose-Einstein condensate of molecules. On the other hand, when the interaction are weaker and attractive, the couple that the two spin atoms, the atoms in the two spins form, it's a Cooper pair, and so below a critical temperature, we have a BCS superfluid of Cooper pairs. And then we can explore also the regime where the scattering length diverges, so the strongly interacting regime where we have that the interaction between particles are the strongest as permitted in nature, which is called the unitary Fermi gas. So these are the different kind of superfluids that we can produce in our lab, and then we use the following tools to manipulate them and to create the current entering geometry. So this is a sketch of our experimental setup. So here you can see that we have the vacuum chamber where we create the atomic cloud, that here is sketched by this red cloud, which is definitely not on scale with respect to the experimental setup. So we have three different tools that allow us to manipulate with a high degree of control our atomic cloud. So the first tool is a high resolution optical microscope objective that you can see here is positioned below the science chamber, and we use it for two things. So the first thing is that we use it to have a high resolution image of our atoms with resonance light that for lithium is red, so at 670 nanometer. And we use the objective also to imprint tailored and arbitrary optical potential on the cloud. In particular, we realize the optical potential with a digital mirror device, which is this device in here, that is consisting on an array of micrometer-sized mirror that can be programmed such that they can shape the intensity profile of a laser beam in an arbitrary manner. So thanks to the DMD, we can tune and we can really sculpt the potential that the atoms feel. And in particular, we use it with blue detune, so repulsive potential for the atoms, so that we can shape the optical potential for them. And finally, the final tool that we use to manipulate our cloud is a TM01-like beam, still with blue detune optical with blue detuned light at 532 nanometer. So this beam is shown on the atoms from a side, and it consists on two light sheets that are repulsive for the atoms, so that they are trapped in the minima of intensity here in the middle. And this beam is used to squeeze the cloud along the vertical direction, such that we have a almost quasi 2D configuration. So actually the motion along the vertical direction is not 2D, but it's oblate enough such that we can have all the cloud along this direction well on focus for our microscope objective. And for example, for what concerns the motion of the vortices, we can regard it as to be 2D. So thanks to this tool, we can create homogeneous optical potential as depicted in here. So for example, if we shine a circular trap on our cloud, we can trap them in this pancake in here, which displays an homogeneous density profile along all direction. And then we can tune the potential with the DMD to imprint and to create any kind of potential. So here, for example, you can see the skyline of Florence drawn with our lithium atoms. So thanks to this device, then we can tune the optical potential of the atoms. And in particular, we use these tools to create our ring geometry as the one in here. So we create our ring, and then we use a phase imprinting technique to excite the current inside the ring. So the phase imprinting technique consists on creating, in our case with the DMD, a light profile that has an azimuthal gradient in the azimuthal direction, and then shine it on the ring just for a small time that we call the imprinting time. So when this happens, a phase is imprinted on the wave function of the superfluid, which is directly proportional to the potential that we created with the light. So in our case, it's directly proportional to in the azimuthal direction. So it is linear in the azimuthal direction, and it's constant in the radial one. So when we imprint a linear gradient in the phase of the superfluid, which gives rise to a velocity. And in particular, the total imprinted phase that we have, that we imprint in our cloud depends linearly on the particular potential that we shine on the cloud and on the imprinting time. So this is the technique that we use to inject the current, and then we have to detect it in some way. To detect the current, in particular, we use an interferometric probe, and we slightly change the geometry of our cloud. So instead of using a simple ring, we also add a central disk inside the ring that provide us a reference for the phase. So then we use a time of flight expansion to make the two superfluids, so the ring superfluid and the disk superfluid, to overlap and show the interference that measures the difference of phase between the two superfluids. And this is what we observe. So when we imprint nothing, so I mean, we really do not turn on our imprinting beam, then we see that the interference pattern that we obtain in time of flight shows concentric rings. That means that the difference of phase between the disk and the ring is constant throughout all the azimuthal coordinate theta. On the other hand, when we imprint a difference of phase, which is exactly 2 pi, and we do it by tuning, in particular, the imprinting time, then we observe that the interferograms that we obtain in time of flight changes into a spiral pattern. And this spiral pattern measures exactly the winding that we have in our system. In particular, thanks to the high resolution that we have in our system, we can not only observe that the interferograms changes between concentric to a spiral one, but we can also directly measure the local phase difference between the two superfluids, just performing a local sinusoidal fit of the fringes that we have in time of flight. So here, for the 3 cases that I'm showing you, you can see that we can measure what's the phase of the ring superfluid, so the relative phase between the ring and the disk superfluid as a function of the azimuthal coordinate, which is constant in the case that we have no current. That means that the phase of the ring superfluid is constant, and so the ring superfluid is at rest. And on the other hand, when we imprint a total phase of 2 pi, we observe that the local phase is linearly changing with the azimuthal coordinate. That means that there is a velocity, since the velocity is proportional to the gradient of the phase. And in particular, we can fit what is the slope of this line that we observe in the local phase, and we obtain a value which is consistent for these two particular cases with +1 and -1, which measures exactly the winding number of our ring superfluid. So with this tool, we can introduce a current into our ring superfluid and we can measure it. And in particular, we are interested in observing when the current is persistent and how many winding we can inject in our ring superfluid that are still persistent. And this is a gallery of all the circulation state, so all the winding that we can obtain in our system. So each row of this plot represents a different interaction strength, so a different superfluid between the BC to the BCS superfluid in our case, where we all, in all cases, we imprint the superfluid current and then we tune the imprinting time to access different winding number that here are measured by the number from the number of the spiral. And for each of the interferograms so for each of the combination of kind of superfluid and winding number that you see here, we observe that the current is persistent in the sense that we can measure the current lifetime just measuring the interferograms as a function of time. And as for this case, there is the winding number 1 for the unitary Fermi gas. So this particular case, we observe that the spiral in the interferograms survives for a very long time, in particular for this data set up to 3 seconds. And it's particularly robust even against the losses of particles. So here you can see that the contrast of the fringes get lower and lower because the atoms have so the superfluid has a finite lifetime, but despite the number of atoms is decaying over time, the current still survives in our superfluid ring. So as you can see in this plot, qualitatively, we observe that the maximum circulation that we observe to be stable in our system is different in the 3 regimes. So in particular, we can access a circulation as high as a winding of 8 for the BC, of 9 for the unitary Fermi gas, and even lower, so up to 6 for the BCS. And this is not particularly surprising in the sense that we know that the different kind of superfluids that we have in our laboratory display different critical velocity. And for example, here I show you a measurement of the critical velocity performed in 2015, and here you can see that the critical velocity is increasing while moving from BC to unitary, to unitarity, and then it drops out when moving to the BCS. So the fact that we observe the highest stable circulation at unitarity is simply a consequence of the fact that the unitary Fermi gas has a highest critical velocity in our system with respect to the others. And then since we are able to excite all these this winding number and we observe them to be stable, we actually want to trigger the decay in a controlled manner such that we can investigate what's the decay mechanism of the persistent current. And to do so, we introduce a local obstacle in the ring that here you can see as this dip in the density of the ring. So we introduce this obstacle and then we excite some circulation, then we ramp up this obstacle and measure what's the winding number as a function of time via the interferograms technique that I showed you before. And here you can see the results for the BC regime of interaction strength. So you can see that there is clearly a critical circulation up to which, actually above which the circulation, the current gets unstable. So for example, here you can see that all the circulation above 5 displays an exponential decay. And if we observe the interferograms during this decay, you can see that the the interference pattern get enriched by some imperfection in the atomic density that are compatible with the presence of vortices. And here I compare our experimental results for the two winding of 8 and 7 with some GPE simulation that we did of exactly our experimental setup. And you can see that here in the, of course, in the GPE simulation, the presence of vortices is even more clear. And then to verify that the decay of the current happens via the emission of vortices, we really counted the number of vortices that we can observe during the decay. So we create the same experimental setup, so the same winding in the same ring, but then we eliminate the central disk such that we can observe more clearly whether in the time of flight expansion of the cloud there exists vortices or not. And so in this ring-only geometry, we can count the number of vortices as a function of time. And here you can see the corresponding measurement of vortices for the different decay that I showed you before. So what we observe is that for each day, every time that the current decays, we observe an increment in the number of vortices, and in particular, the total number of vortices that we observe, in our ring scales linearly. I mean, it's proportional to the number of winding that we lose from the current, meaning that actually the decay of our persistent current happens via the emission of vortices, and in particular, each vortex that is emitted in the superfluid bulk brings away one quantum of circulation from the persistent current. So, and to verify this interpretation, we use our GPE simulation to understand better what is the microscopic mechanism of the supercurrent decay in our system. So in the GPE simulation, we measure what is the local velocity of the superfluid in the midpoint between the internal ring radius and the obstacle position, and we compare it with the local speed of sound of the superfluid that you can see plotted in these two plots in here, below the critical winding and above the critical winding. So when we are below the critical winding, we observe that the superfluid velocity, which is plotted here in black, is always below the local speed of sound. So no excitation is emitted, excited in the superfluid ring, and the current is stable. On the other hand, when we have that the winding is above the critical winding, the local speed of sound, the local velocity of the superfluid displays this non-monotonic trend for which there are at certain moments the superfluid velocity is above the local speed of sound. And in this case, a superfluid, we observe in the superfluid density that this corresponds to the moment of the emission of one vortex in the superfluid ring that determines a phase ellipse that brings down again the superfluid velocity, and so on and so forth. Then the superfluid velocity increases again, and when it exceeds the local speed of sound, a second vortex is emitted, and so on and so forth. And in particular, the microscopic vortex emission process is displayed in this time sequence in here, obtained from GPE simulation. So you can see that actually in the density of the ring, the presence of the obstacle creates a channel between the obstacle and the internal ring radius that displays a lower density with respect to the superfluid bulk, and the lower density here diminishes the speed of sound such that then for high enough speed of the superfluid, the local speed of sound is exceeded and a vortex enters from the inside of the ring and travels the superfluid density itself. And when this happens, exactly one quantum of circulation is removed from the current and is acquired by the vortices. So we repeated this experiment. Oh, sorry, one plot is missing. Okay, we repeated this experiment, triggering the decay of the supercurrents with the different superfluids that we have in our lab. So from BC, in the BCS crossover. And this is the results that we obtain where I plot the value of the final circulation after the decay as a function of the initial one. And as you can see, the BC shows a clear critical current roughly at a circulation of 5, and the BCS as well. Whereas the unitary Fermi gas is observed to be particularly robust against the defect that we introduced in the density, because none of the circulation that we could access actually displays a decay. So for this first part, I would like just to provide a short conclusion. So with the method that I explained to you, we are able to imprint an arbitrary winding number, so an arbitrary circulation in our ring superfluid, and we can measure with interferometric probe. And then we demonstrated that the instability of the current is goes along with the emission of quantized vortices that are strictly connected with the decay of the current. So now I would like to slightly change topic and move on the second work that I would like to present that regards the Kelvin-Helmholtz instability. So in this case, we are considering two counterflowing superfluids that moves with a well-defined difference of velocity along an interface. And here you can see a sketch of the Kelvin-Helmholtz instability for classical fluids. So when you have two superfluids that moves with different velocity, any fluctuation can give rise to excitation in the interface that divides the two superfluid, and these excitation are wave-like excitation of very well-defined mode at wave vector k. And when this fluctuation enters into the game, then the modes at well-defined k can be can grow, and in particular it grows exponentially, such that then we have this rolling up dynamic on the interface between the two superfluids that give rise to the Kelvin-Helmholtz instability. So the Kelvin-Helmholtz instability, it's an instability of the interface between two counterflowing fluids that displays an exponential, that displays some wave-like excitation with an exponential growth that can, with a growth rate that can be parameterized in this way, for example, in the treatment that was done by Rayleigh almost more than 1 century ago. So the growth rate here, as you can see, depends on the difference of on the velocity difference between the two superfluids and on the thickness of the interface. And the Kelvin-Helmholtz instability, it's a very broad phenomenon that regards different aspects, let's say that regards different phenomena in nature. And here I would like to just to tell you the most famous two. For example, you can see Kelvin-Helmholtz instability in the clouds when there are two fluids of air at different density moving one against the other, and here it's represented by this curly shape of the clouds. And as well, you can see the Kelvin-Helmholtz instability in the surface of Jupiter, and here it's represented by this image. Okay, so this is let's say the classical Kelvin-Helmholtz instability, and we would like to see how and if the Kelvin-Helmholtz instability changes when we try to study the counterflow in superfluids. So the Kelvin-Helmholtz instability have been studied for superfluids of two components that can be either an instability between the normal and the superfluid component of the same superfluid, or as the plot, as the sketch in here, sorry, as the results in here for numerical results as for the at the interference between two components BC. And as well as for the classical image that I showed you, you can see that when there is a counterflow, the interface between the two superfluid develops an instability that grows in time and then creates this specific particular sawtooth pattern. And on the other hand, we can investigate the Kelvin-Helmholtz instability also with a single component superfluid. So, for example, in this theoretical work, they studied the counterflow between the same superfluid over a barrier. And in this case, what happened is that when the interface between the two parts of the superfluid is removed, then the superfluid develops vortices. And in particular, this is simply given by the phase profile of the moving superfluids that have at the interface. So if we have two superfluids that are moving in opposite direction, then they should have an opposite gradient in the phase. And then when they are merged, the gradient in the phase develops also, let's say, in a circular way along this line, such that a vortex is created. And in particular, when the number of vortices is proportional to the velocity difference, because it's proportional to the different phase gradient between the two superfluids. So these are the exploration that were performed, and we tried to measure it in our experiment, slightly changing the geometry. So as I told you here, were considered two laminar flow of superfluids in opposite direction, but what is more natural from the experimental point of view is rather to create, oh, sorry, I missed one part. So what I forgot to tell you is that so in one single component superfluid, the interface is represented by vortices. So what is the interface, let's say, distinguishing the two superfluids in the classical regime? In the superfluid, in one single superfluid mode, this is the interface is represented by the vortices. So actually, we can track the position and the stability or instability of the interface by tracking the vortex position. And given that the interface is given, displayed, it manifests itself with vortices, we can use a point vortex model to understand and study the Kelvin-Helmholtz instability. So in particular, by studying the Kelvin-Helmholtz instability with the point vortex model, we also see that the interface displays some wave-like excitation at well-specific wave number. And in particular, this excitation grows exponentially in time with a growth rate that is given by this formula in here, where here it appears the parameter dV, which is the distance between the vortices at the initial time. So with this point vortex model treatment, we observe that the growth rate has to have this trend. So there exists a maximal growth rate that happens for a very particular wave vector of the excitation. And in particular, this growth rate has a scales quadratically with the difference of velocity between the two superfluids. And this gives us a way to demonstrate, let's say, to observe and clearly determine the nature of the instability as Kelvin-Helmholtz instability in our system, because if the growth rate, the maximum growth rate that we measure scales quadratically with the velocity, then we can say that there exists a Kelvin-Helmholtz instability. So as I started to tell you before, speaking about this slide, actually in the experiment, we do not use this laminar flow geometry, because it would have some accumulation of the density at the boundaries of the trap, but rather we use a circular and a ring geometry as the one in here. So in particular, we use the technique that I showed you before to excite well-defined winding number in the two ring, and in particular we excite opposite winding number in the internal and the external ring. This gives us a way to tune the velocity at the interface, which is simply given by the difference between the winding number at the radius of the interface of the barrier in here. And then after that we have excited this current, we remove the barrier. And in particularly, as a function of the height of the barrier, this is what we observe. So if we suddenly remove the barrier and we observe the time of flight expansion of our two-ring superfluid, then we observe an interferometric pattern which is very similar to the interferograms that I showed you before, because this kind of pattern measures exactly the difference in winding between the internal and the external ring. And this is a way for us to measure what is our initial condition. Then if we remove more, so if we decrease the intensity of the barrier linearly, we see that this interference pattern changes into a pattern of vortices. So if we remove gradually the barrier, then we allow the two superfluids to merge, and then they display the vortices that are given by the phase constraint between the two superfluids. And in particular, we observe as many vortices, as many difference, winding difference, so this delta W that I showed you in here. So this is our starting point. So when we remove the barrier, we have that the interface between the two superfluids is given by this array of vortices, which we call the vortex necklace. And this is, in this particular case, in this initial case, the vortices display an ordered structure, which means that the interface between the two superfluids is stable. Then to observe the Kelvin-Helmholtz instability, actually, we investigated whether this vortex necklace is stable or not by monitoring its evolution in time. And here you can see 3 examples of the evolution of the vortex necklace for the 3 different superfluids that we can explore, and for different initial winding from 6 to 10. And in all cases that you can see in here, we observe that the necklace is actually unstable over time, and actually it displays a similar rolling up dynamics resembling the one of the Kelvin-Helmholtz instability. And here you can see it for the BEC superfluid, but also a bit less clearly is visible for the unitary Fermi gas and for the BCS superfluid. And to quantitatively estimate the nature of the instability that we observe, we measure the angular structure factor. So for each time we track the vortex position, and then we build the angular structure factor that measures the presence of excitation of the interface at different mode that here we label as M. So for example, for the unitary Fermi gas, this is the time evolution of the angular structure factor that we observe. So as you can see in this plot here, when we start, the angular structure factor is centered to one single mode, which for this particular case is centered around 12 for preparation of a difference of winding exactly of 12, because at 0 time we have a perfectly ordered lattice of vortices, which displays exactly this mode. And then if we let the system to evolve, we observe that this mode actually moves towards the lowest value of M, and then it diminishes its amplitude as we travel in time. Then we can select a single mode. So for example, for this particular data, we can select the mode at M equal to 6, and we can track what is the evolution in time of the angular structure factor that here is reported in log scale. So as you can see, for example, for this particular mode, we observe an exponential growth of the mode, which is consistent with the exponential growth expected with by the Kelvin-Helmholtz instability. And in particular, we extract from with a linear fit the growth rate for the particular mode M, which we call sigma M. Then we study what is the evolution or what is the growth rate for the different modes in the different regimes. So here you can see what are the measured values the measured values of the the growth rate of the angular structure factor in the different regime of BC, unitary Fermi gas, and BCS, and they are compared with the Rayleigh growth rate in purple and with the point vortex model expectation for the growth rate in black. So as you can see, they all display the same behavior of the growth rate as a function of m, and the different symbols here represents different initial condition in terms of delta W. So all of them, they display this trend with a clear maximum growth rate for a well-defined value of m. And in particular, we can analyze what is the scaling of this maximum growth rate sigma star, so to understand the nature of our instability. And here are, I show you our results. So I plot the maximum growth rate for the vortex necklace instability as a function of the square of the velocity, or the difference of the velocity difference in the initial condition. And as you can see, they show the trend of the sigma star is linear with delta with the square of the velocity, and this is exactly what we expected from the analysis of the Kelvin-Helmholtz instability with the point vortex model. So the observation of this trend verifies that the instability that we observe is the Kelvin-Helmholtz instability. And here we compare it with the different theories. So again, with the Rayleigh expectation and the point vortex model, and with numerical simulation with Gross-Pitayevsky equation, and with the Zaremba-Niguni-Griffin method. And as you can see, actually the experimental data shows that a growth rate which is not compatible with the theory expectation, and it's actually lower. And this is consistent with the presence of extra dissipation mechanism in our setup, which are expected to decrease the growth rate of the Kelvin-Helmholtz instability. So with this measurement, we, by verifying the scaling, the quadratic scaling of the maximum growth rate with the velocity difference within our two-ring superfluid, we verified that we observed the Kelvin-Helmholtz instability in our system. And this brings me to the conclusion. I reported on two different experiments that we have performed in Florence regarding the stability and the instability of the currents in ring superfluids. So in the first experiment, I showed you that actually the current that we can populate in our fermionic rings, they are particularly stable, so they are observed to survive for a very long time, and they are robust against the losses of atoms. And then we trigger the decay of the current with an impurity, observing a critical behavior in the different regimes of superfluidity that you observe, that it's consistent with the expected critical velocity trend in this different regime. And on the other hand, we explore what's the instability when two counter-propagating superfluids are merged. And I hope I convinced you that thanks to our analysis of the angular structure factor and the maximum growth rate, we observed the Kelvin-Helmholtz instability in our system. So really the last slide, let me thank the broad experimental setup, experimental group that worked together with me in this setup. So our PI Giacomo Roati and the many PhDs and postdocs that have been working with me in this time. And these are work have also I've also been supported by some theory collaboration with the people here. And with this, thank you for your attention.
All right, thank you very much for the nice talk. I see we already have at least one person with a raised hand. If anyone else has questions, raise your hand or pop it in the chat. Luca, do you want to start?
Yes, okay. Thanks a lot for your nice talk. At the beginning, you were showing a diagram of the BCS-BC crossover, where there was the superfluid part and the normal part separated by the critical temperature.
Yeah.
And if I have seen correctly, in your plot, the critical temperature is monotonous. It does not have a local maximum, because in other, usually sometimes people plots the curve, the solid one, let's say, and usually at close to unitarity there is a local maximum, and instead the behavior here of the curve is monotonic. So can you comment about this?
Yes, yeah. So you are referring to this critical temperature here that
Yes.
so there are some some theoretical work and that predicts a peak close by unitarity. So for this particular plot, I used the theoretical curve developed in the group of Camerino, where they use a T matrix. Sorry, it's going to be particularly precise, where they use a T matrix methods to estimate it. So let's say
Piaggio Pieri with Strinati.
Exactly that.
Okay, I see.
Yeah, it's a recent work. The first author is Michele Fini. And I mean, at the time that I draw this phase diagram, that was the most recent, and it was also compatible with some, let's say, preliminary and I mean, not super precise experimental observation that we had in our lab, performed with a different technique. So with Josephson effect, we investigated what's the critical temperature of the breakdown of the Josephson effect, and we found that it's compatible. I mean, not in quantitative agreement, but compatible with this theory. So that's the reason why I decided for it.
Well, I have also another question, if I can. Okay, yes. Well, you were showing, say, circular rings, but is it possible to create rings which have, say, ellipsoidal ones? Yeah. Is it possible? Do you expect something new in that case?
So in principle, we were considering actually to move on some more exotic geometry, and in particular, let's say, I think it's called the billiard one could be particularly of interest, and in principle, yeah, I mean, also this particular geometry should display persistent current, and it would be nice to develop. So the experimental setup that we have, yes, it's let's say well suited to perform this kind of experiment, because the geometry of the atoms is completely freely tunable, okay, under certain constraint, but over a good degree it's tunable. And yeah, so it would be nice to explore different ones, but I have no news yet.
Okay, thank you. Thanks a lot.
Thank you.
So I have a question as well. So I know there are a number of different ways to make persistent currents in the BEC, and the one you have is quite nice. I'm curious though, do you end up in situations where you actually end up having vortices that are imprinted as well, in addition to your persistent current? Because that's often a problem with some of the other techniques.
Yeah, that's also our problem. And it's a small problem for us, because as you can see, so let's say the problem originates from the fact that dealing with a real machine, you will never be able to imprint exactly a gradient in the phase. So as you can see from this experimental profile of the gradient we are imprinting on the atoms, there is also, let's say, a small anti-gradient in the opposite direction, which is given by the finite resolution of our imaging system. So because of the presence of this anti-gradient, we actually introduce some unwanted excitation in the density of the ring every time that we that we perform an imprinting pulse. The important thing, let's say, what we found out is that actually for us this is not a big problem, because these excitations are small enough that for all the currents that we observe to be persistent, actually they just introduce some vortex or some sound wave in the density of the superfluid that survives on top of the current without disturbing it. But actually we observed, so let's say we performed some GPE simulation to see whether we can, whether the maximum current that we can excite in our ring is consistent with what to expect. And we saw that this current is actually limited by the presence of this excitation. So for example, I'm sorry, for these currents that I draw here as unstable, what happens is that the excitation that we introduce by our imperfect imprinting actually are such that one vortex that resides in the inside of the ring has, let's say, can easily, enter into the superfluid bulk density, removing one quantum of the circulation. So actually, we would expect to have also, to access also to higher winding if we could get rid of these. But in our case, it's small enough that we could anyway use it to explore quite widely the winding number.
Okay, thank you. Davide, do you have a question?
Yes, I do. Thank you, Kelly. Thank you, Giulia. So I missed the first part of your talk, so maybe you said that, but can you comment a bit more on the dissipative mechanism that that you mentioned at the end, that show you that you cannot really see the
you mean for the Kelvin-Helmholtz
predictions?
No, I didn't comment before, so thanks for your question. So actually, so let me move quickly on the plot that we are referring to. I'm sorry. So here, yeah. So what is expected also from a classical point of view is that the, let's say, dissipation or some other effect also related to temperature could actually slow down the Kelvin-Helmholtz instability, so actually reducing the growth rate that we observe. So in our particular case, as I told you probably quickly, the red dots in here are a numerical simulation that includes a finite temperature of our system with the Zarembani-Cooney-Griffin method. So actually what we observe is that even introducing a temperature effect in our system is not enough to bridge the gap that we observe between the theory and experimental results. So actually there should be some other mechanism, at least in the BEC, where the theory that we have implemented is well known to be precise. And these mechanisms could actually be connected with the previous question. So we imprint the current in a way that it's not perfect. So we know that for every imprinting, we also introduce some vortices in the superfluid bulk. There are not, let's say, the vortices that tracks the interface of the Kelvin-Helmholtz instability. So we tune our experimental parameters such to minimize this number of vortices. But anyway, there are experimental fluctuations. So I mean, in some of these, I mean, in almost overall, in all the data set, there will be a finite number of, let's say, spurious vortices in our system that could provide the dissipation mechanism. And on top of it, I mean, even if not vortices, we know that we excite also some density excitation, which could have some effect for what regards the BEC. And for what regards instead the BCS, it could also be, for that particular case, the temperature itself, which could have a more striking effect in this regime with respect to the others. So actually, we cannot identify exactly the source of dissipation that that give us this discrepancy. We have a few candidates, and it would be super interesting to dig a bit more. For example, investigating what's the effect of temperature in the different superfluids, and so on and so forth.
Okay, thank you. And I wonder, have you tried to make this plot in log-log scale? I know that you have a very well, a few points, but just to see if it's a linear behavior or if it's something else.
No, actually, we didn't try. Let's say, not that I remember.
Okay.
Yeah. One thing that we tried, let's say, is rescaling our understand what is the rescaling factor between our experimental data that would bridge the difference between the experimental and the theory. And this factor in particular, we observed that it's constant from BEC up to unitarity, and then it increases or decreases up depending on how you see it when you go to the BCS. And now we are performing also some measurements to understand what's the dissipation, let's say how the dissipation happens into vortices, also inside the point vortex model. So trying to understand what's the value of the dissipation parameter alpha and alpha prime, sorry if I'm speaking like this, in the point vortex model to see whether we should expect a striking difference when moving from BC to BCS.
Okay, well, thank you. Really nice work.
Thank you.
Thank you.
Thanks.